He bought a lot of money.
Okay, guys.
He does.
Ready?
Yeah.
The article is first one.
So we're starting, right?
Yeah.
Just, I think I should just. We were trying to find out the partition function for the free Klein-Gordon field theory whose Lagrangian is this, and this Lagrangian is written in this metric convention, just in case you forgot. And we found the partition function to be this. We used Diana-Baumann trick, a bit modified Diana-Baumann trick to find this. The proper way to do it is in Srednicki, chapter 7. That's using Fourier transforms. That's problem number 2 of PQ's homework. And I think in the notes I uploaded, I've done it as well, but it's the same thing. And then to organize this thing, we introduced pictures. So this delta is represented by a line with 2 endpoints. If it's delta to x minus y, then it's just x to y a line. And there's a 1/i factor for good luck. And this blob with no index specified on this is an integral of the source.
That is not one. So does that only work with a 2-point Green's function? Or
This one?
yes.
Yeah.
Okay.
This is just for a 2-point Green's function. And there is an I factor also. So with this pictures, we can write blob, line blob to be what? This blob is just I integral x jx, and this other blob is I integral y jy. We are using 2 different integration variables, and then you have a propagator in between, and we've said this is x and this is y, so it's 1/i delta x minus y. Is that clear? Is there questions about that? That's all right, right? Then you can cancel one i's off, and then you get integral x y, this thing which you had on top of the exponential. So you can write z naught of j in terms of this picture. It's exponential half blob. And then we had the rule for a functional derivative of a picture, which is just 1/i d by dx djx on this picture. And you have, these are sources, right? There are 2 possible sources here. So this is sort of like source squared. That gives you a factor of 2. And then you remove one source and attach the label x to that one. Then we derive the Wick's theorem for a 4-point correlation function, which is just the time ordered expectation value of 4 field operators at different points. So this is equal to, by definition, d1, d2, d3, d4 on z0, and in the end we set j equal to 0. And where delta 1 is just a shorthand for 1/i d by d jx1, because this is too much to write. So how did we derive it? We derived it in a dumb way. We took differentiation of this z0, which is an exponential, so that had a lot of terms, got ugly. The easier way to do it is to first expand the exponential. The exponential, as we all know, is just 1 plus x plus 1 by 2 factorial x squared plus blah blah blah. Here x is just 1 by 2 blah blah. So the z0 j expands to 1 plus half blah blah plus 1 by 2 factorial half blah blah squared plus 1 by 3 factorial half blah blah cubed, and so on. Now we want to take 4 derivatives of it, right? 4 derivatives with respect to j. So any term before this goes to 0 after 4 derivatives. Because, for example, in this term, you have 2 j's. You exhaust all the j's after the first 2 derivatives, then the rest do not depend on j. So the derivative is 0. Any term after the 1 by 2 factorial term also goes to 0 in the end when you set j equal to 0. Because this has how many j's?
6.
This has 6 j's and you have 4 derivatives. So in the end you will have 2 j's left over. When you set j to 0, boom, gone. So you just have to take 4 derivatives of this term, which is extremely easy. So I leave it as an exercise for the reader. We derived this in the hard way, so it should be easy. And how do you take the derivative? Here's the rule. And how do you take the derivative of this guy? What is this?
It's x to y.
It's just x to y. This is also a reminder. Now let's get to business for today. We want to do this theory, which is what PQ is doing, I think, right? Svetnik is doing phi 3 theory, which is pathological in some reason in 4 dimensions. But let's do it for phi 4. But before that, let's do it generally. What we want to compute is a partition function. Right? What's the definition of this? How do you compute this? Somebody say something. What? Yeah. It's the path integral, right? It's sum over all paths, all possible configurations of the field, exponential, what?
Yes. Standard.
Action. And the action is just this, right?
Right.
Now I decompose my Lagrangian for the, no, that's not all. This. Because I'm computing it for a source. Now I decompose the Lagrangian into 2 parts. One is the free Lagrangian, which is just this. Then an interacting Lagrangian. So I write it as it would be nice if we could reuse this result somehow. Can anyone see a trick here?
Last time we did only L plus J something like that.
Yeah, we just did L naught plus J. This L1, whoops, L1. L1 could be lambda by 4 factorial 5 to the 4, which is the theory we are interested in. Can anyone see a trick to make use of this result?
You do integration by parts or something?
No.
Maybe you can redefine your field, phi naught plus something, deviation, something.
No.
No, you can just separate the exponentials.
Yes. That's the idea.
What is it?
So I write this as integral d phi.
What it is. That's okay.
So these are all numbers, right? There are no operators, so I can just swap them around as I please. So I write it as exponential of I integral x L1 of phi, then exponential I integral x L0 plus j phi. Too many brackets. Didn't achieve anything. I just separated the L1 part. Now can you think of it?
the clue is
Yeah.
right here. So remember, this was equal to oops.
So I guess write L1 of phi as derivative of j.
That's the trick. So you write this as, you bring this guy outside. Then what's left?
ZJ.
Oops.
No.
Is that step clear? Maybe not, right?
So we
Phi
rewrote.
is the functional derivative of j,
Mm-hmm.
but it just gives you a phi term, right? You need phi
Let me
force.
try to elaborate. So
That is like the function of L1, right?
how do you compute this?
Isn't that supposed to mean like L1
Yeah.
of?
Whoops, yeah. 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 How do you compute this? Let's just go step by step. In terms of Z naught. We did that for 4 terms.
Yeah, just take one functional derivative.
It's just 1 over I djx integrate d phi. Oops. Right? I mean, even without this,
Yeah.
if this is with reaction with J, this is true, right?
Right.
Is that alright? Now, how do I compute this?
Another functional derivative.
Oh, that's a square.
Oh, it's a square.
I thought it was a tilde.
I thought it's a tilde as well. But you got it.
Yeah.
Terrible handwriting.
So.
Is that clear?
Yeah.
Right?
Oh.
So, how do you compute this?
Nice.
E to the I.
It's e to the I, oops, e to the 1 over I p djx on z naught of g, right? It's alright?
So it's a function of an operator.
Yeah. But is this clear? That's my question.
Yeah.
Then how do you compute this?
E to the power 1 over I f.
Yeah.
It's basically the same description we use to define quantum mechanics. To replace the observable by the operator. Roughly speaking, very loosely.
These are not operators in the operator, quantum mechanical operators.
Right,
This is a
right.
differential operator,
Yeah, but
which acts on numbers.
yeah, but it's
No.
roughly the same idea. You just replace the
No, but how do you compute?
f of a 1 over I d by d.
That's clear. Now is this clear?
That is not clear. The last thing that
So this is clear, right?
Yeah.
So this is clear.
Yeah.
So if you have a function, so what you have here is e to the phi.
Yes.
So what did I do here to the next step? I replaced phi by 1 by I d by djx, okay? And the function remains the same. So instead of e, if I think about a general function f, then I replace phi in the function by, you know, if f was e to the power, then I get this. If f was whatever inside squared, I get that. So it's general.
So then in this step, just to the left, f of phi is what? E to the I integral of L1 phi.
Yeah, I will rewrite it properly here. So that step is clear. Then integral d phi exponential of phi integral x L1 phi. This is equal to, this is again a function of phi, right?
Yeah.
Which I take outside. Exponential phi integral x L1 of 1 over I dx. And this was ZG. Is that all right?
Yes.
Now we can just make use of this guy that we already found to get the results.
Ravi?
Yeah.
Can this be done for any function form of L?
What do you mean? Do you have a
I mean-
specific example in mind?
Yeah, that's what I was thinking, like, in general, whatever additional terms that will be added to the diagram, they should have some phi of the form phi to the power n.
Yeah.
So that will work for that for sure.
Yeah.
But if there is something like, which has negative powers of phi,
That's
And
like
in general,
Taylor
that-
extensions.
I see.
I
Negative
think,
ones.
I think you can show that this will be true for any Taylor expandable function.
Yeah.
Right? But I don't know if that's not true, because the way to properly prove that is Taylor expanding both exponentials in the right and left hand side of the equation, and then using like power by power, the thing that you said, whenever you have phi to some power, then for sure this expansion is valid, right? You can just put it out, replacing phi by one of derivative. I think we should simply assume that every potential is Taylor expandable.
Yeah, if the potential is, say, for example, log phi or something, I don't think it has. Yeah, that's still Taylor expandable. If
No,
it's
one
1
is-
over phi, let's say, is that an interesting potential to work with? I don't know. I don't think it is.
Never seen.
Yeah,
yeah, this is, yeah, I think it,
that's definitely going to be non-renormalizable, which is something we'll discuss probably next week. Maybe not next week. That's
Would that be normal?
Yeah, the mass dimensions will be a bit tricky, right?
Okay,
Let's think about it later.
Yeah, I'll think about it. There should be some other, there should be some constraint.
Yeah.
At least, I would expect something that can be Taylor expandable, because we have this nice picture of fluids interacting at a local point, and when you have like phi to some power, that means, I mean, he'll get to that already, like phi to the n, or n fields, connecting in the same space-time point, that will give rise to the vertex. I didn't wanna say this word, cause it doesn't make sense yet. It's still gonna get there.
So let's go to our solid example, which is this. So we're going to construct ZJ to lambda phi 4. So what's it going to be? We wrote it down for a general program, so it should be easy.
So you just replace the phi with whatever this new thing is. Yeah. Whenever I delta delta
Exponential
j.
just lambda by 4 factorial 5 to the 4th, and I replace 5 to the 4th by the partial derivatives. So how do you compute this? It's all nice and clean, but to compute this you have to expand this, right? So this is equal to, let's expand this exponential first as a power series. This is nothing but this is the expansion of the exponential, and now this guy we have already computed here, right? So we can just use that. Is that all right?
I think there is a detail that might be important to tell them now, that this expansion of the exponent, we've gotta be very careful with the variables we're integrating over.
Right.
Because if you have, like, to the power 2, we have 4 derivatives applied into x1, let's say, and 4 more applied into x2. We gotta integrate over 2 different variables, not just
Yeah.
the same.
What he said is this. So for v equals 2 term, right? You have something like this. Right? What does it mean?
Should be 4 derivative to the constant. I thought it just meant 8 derivatives.
Hmm?
I thought it meant 8 derivatives.
It's not. It means integral x1 and the 4 factorial by L j x1 to the power 4
Times
D and X2.
multiplied by x2 and the 4 factorial by L to the power 4. So this is a schematic notation. This is understood. If you have v terms, it's 1 over x1 blah, 1 over x2 blah, till 1 over x integral xv blah. Same goes here. Right? So yeah, let's just analyze this for a bit. If you take a particular term with a fixed v and a fixed p, in the end, how many sources will be left out? That is called the number of sources that's going to be left out after all the derivatives to be e. What's that number going to be?
p minus v for a particular term.
True. How many sources are here? That's 2p sources, right? And how many derivatives are we taking? 4v. So this is the number of sources that's going to be left out in the end. So these variable namings are indicative of something. So p indicates the number of propagators in the diagram because you can sort of see it. And v indicates the number of vertices in this diagram, which will be clear by the end of today. and E will correspond to the number of external lines, which will also be clear by the end of the day. Yeah, but the rest of this analysis is, I think, pointless. Let's go and compute stuff. Let's get to
Yeah, I'm confused with this number of sources. I thought it should be 2 to the power P and 4 to the power V.
no. How many sources are here?
2.
Yeah. So if you take power of P, then no. It's 2P, right? Let's say you have 2 here.
Yeah,
Let's say we have 3 here.
yeah.
Do we have 8 sources or 6 sources?
So we have 1 integral, 2 integral, 3 integral.
Mm-hmm.
2
6
from
sources.
each. 6. Okay.
So it's 2P, not 2 to the P. Okay. Simple. So let's fix some V and P, then see what these terms are giving us. I mean, these are all terms in the expansion. It's impossible to compute every term in the expansion. So the idea is we'll look at simple cases and we'll come up with a rule so that we can draw all diagrams at once. Not at once, with patience. This is the easiest case to look at. We have 0 these and then 1 these. What's the term? Let's call it E1 or something.
It's just 2 blobs.
So it's there now. Oh, sorry, the first term. Oh, P is also 1. Right, so it's just 1 probability.
Yeah, we just have this guy, right?
Yeah.
This is just I by 2 into the y v gy 1 minus v jz, right? Right. What is the factor here? What's this in terms of a diagram?
2 source line source.
Yeah, we had that somewhere here. Yeah, we have it here. Right? And you have a factor of 2 y. So it's just half blob blob. That was easy. Now let's look at the harder one. Which one should I go for? Okay, this is going to be very interesting, this calculation. So let's go for I have most likely messed up my factors in this thing, so let's hopefully figure it out here. So V equals 1 and P equals 4. So what's the term we are trying to compute? Just say it out loud.
I integral x lambda over 4 factorial 1 over I delta delta j to the 4th.
Slowly.
Okay.
I lambda over 4 factorial.
What happened to you, man?
I'm just saying the terms.
I lambda 4 factorial, what's next?
So now
I
we have-
lambda 4 factorial, V is 1.
Right.
So this is also 1, this is 1. Right?
Yeah.
And then
So we have to do it.
integral x,
Yes. And the
1 by I d by djx to the 4th,
Yeah.
which I'm going to write as dx to the 4th. Right? Then what?
A lot of stuff. Would you like me to say it?
Slowly. Go.
4.
It's sort of just 4 factorial.
So it's 1 over 4 factorial.
We need I to the 4th.
This thing to the power 4, right?
Right.
But this thing I'm going to write it as 1 by 2 blob blob. Yeah, there should be 4 terms. So it's 1 by 2 blob blob.
What about the summation of the
Yeah, I'm just fixing these. I'm just looking at this term.
of P equals 4 term? So we would also need to do. P
I'm not
equals 4 term.
summing up to 4. I'm looking at V equal to 1, P equal to 4 term.
Oh,
Okay.
Fix,
The T1.
okay.
right?
Yeah.
I was literally like.
Literally, literally fixing it.
This is clear, right? This is now clear.
What was the easy example? V equals 0?
V equals 0, P equals 1.
I guess.
1 propagator, no vertices.
Okay.
So this is going to have 1 vertex and 4 propagators. So my idea is to get to this diagonal and some other. So let's compute this slowly. So I'm going to keep all these factors intact without cancelling it off at any time. The idea is to get at symmetry factors, but I don't think I'll be able to do that. Let's see. 4 factorial, 1 by 2 to the 4, integral x, d4x, and d4x again is 1 over I d by djx log QFT. Now let's compute it. I don't want to write all this time things over and over again, so let's compute integral x. Okay. Let's take first one derivative. Somebody tell me what it is. Yeah, that's just tell me what it is.
Integral x.
Integral x. I took one derivative, it's d3.
dx.
d3x
4 times
4 times
blob blob
blob blob
cube
cube
times
times
line dot
Oh,
1
you're
straight
forgetting
line to
two.
the blob.
If you're into,
this,
if you're in factor of
and
2
there's a
times,
factor of 2,
Oh yes.
which is 2, and what should I write here?
X1.
X,
Okay.
just x, right? And
Okay.
integral x, all the derivatives are.
No, I thought when you write x to the 4, it's x1, x2.
No, it's integral x,
Okay, okay, yeah.
right?
That's very important.
Because for the integral, the notation is different when you write.
If I write integral x something, the whole square, that's integral x1.
Yeah.
So if it's, yeah. So this step should be easy.
Yeah.
Now let's compute the next. So that's equal to. So I will take a 4 times 2 outside. Integral x, yeah. Now somebody else tell
I
me.
have a question.
Yeah.
I'm gonna set blob things to 0 again,
No, we are computing zj, right?
so we will keep all the terms.
Yeah. Yeah. Somebody else tell me the next.
3 times quantity blob blob squared.
3
Yeah.
blob blob
Squared
squared
times the x to blob,
times x to blob.
and then like plus.
That's
Oh.
Square and 2. You're missing,
This guy, right?
you're missing factor of 2 and square.
Yeah.
Fuck man.
So this
You're
is
right.
2 times this,
Whole thing
Right.
squared.
and there is another x2 blob, right?
Right.
Right.
Right. That's right. But that's not all, isn't it?
That's not all, but let me introduce a notation here already.
I guess.
these endpoints, what happened?
You're not listening to the audience.
She already told you times.
Oh, sorry. What were you saying?
Del X square.
You're missing del x square.
Yeah, sure.
And there is an addition, right?
No.
There are two terms. Right?
Yeah.
There are two terms which I'm going to write now. But before that, let me introduce a notation. Both these endpoints are the same, right?
Yes.
It's this is X, right? No, that's yeah. I fucked myself.
The joke is writing itself.
So what was I saying? Yeah, these both labels are X, right?
Yeah.
So I can connect these both blobs to the same point and just call it X. So I'm going to erase this, and there's a 2.
Wait, this.
Oh, that's nice, I get it.
You can write that as square
It
and
has
square.
fine,
What is so fun? What?
Square
It
as
makes complete sense.
You can write it as a square as well,
Why is this better?
Oh.
Yeah.
because you'll see soon.
No, I think you can see from there as well, right? X is the same space-time point. So
Yeah.
it's reasonable to, if you wanna draw some sort of diagram, to put them in the same.
Yeah, you have X to blob, X to blob. Okay,
Yeah.
both X are the same, so you.
I know how to take derivative of that thing,
Mhm.
but I don't know how to take derivative of that thing. I will have to think on that thing.
Oh,
that's
okay,
a good point.
So, yeah, you can leave it as it is, and then in the end, you make
Yes.
this identification.
Yeah. So I
At
will
some
tell you a
point,
rule to
You
take
get
the
used to
derivative.
these ones as well, probably.
Hmm?
To take derivative of this one, you will get used to it probably something.
Yeah, immediately in the next step you'll get used to it because I'll tell you the rule. It's pretty easy.
I mean,
Yeah.
the derivative just depends on the source, and here also you have just two sources.
Yes.
Exactly. So get a
That's
factor of
simple.
2.
Just simple.
Simple.
That's it. So yeah, go ahead.
So that picture,
Mhm.
is it same as that thing in the upper box?
This box?
Yes.
No.
No?
There's a point in the middle.
There's a point in the middle.
Oh,
That's why I was careful to draw it like that.
okay.
Can I rotate that?
Yeah. So plus, what's the other term? Maria will say it.
So, one line.
You have this thing
Yeah, that
first,
is
right?
4.
4, I took it outside.
Then cube of
Blob,
blob.
blob, cube,
And line. Just
and
line.
then
X line, right?
it's X,
X.
X. But both are the same point, man, so why not?
Dude.
What happened?
Then
Let's
that-
quickly
Is that clear?
No, it's not.
Yeah, that makes a lot of sense actually. It makes a lot of sense.
So you're leaving this guy and taking the derivative of that guy, right? So when you take the derivative of this guy,
Angle?
you remove the source
Mhm.
So really
and
just-
replace that by the space-time point, right? Which is what?
Same.
Which is X, right? So this is a propagator from X to X.
um,
So instead of doing this, I write it as
Okay.
X. Is that clear now?
Yeah, and that factor of 2, isn't it taken care of by the factor of 2 outside the integral?
Which factor? I see. No, because when you take a derivative of this again,
Mhm.
right, you get a 3 blob squared and it's a 2
Okay.
and then X blob.
Okay, cool.
Just take the derivative of this guy. Is that clear? Or should I explicitly write it? I can do it. Say it fast. So wasting time. Right, there you go. dx of blob cube, right?
Yeah.
This is 3 blob squared times dx of blob,
Oh,
and this, what is the result of this? Is 2 times,
oh, okay.
right?
No.
Now let's take another derivative of this guy. So we have 4 times 2 integral x dx. who wants to?
GG.
Who wants to take another derivative?
GG.
Let me pull it 3 times 78. And what?
2 times line log,
2 times
line log,
log,
And 2 times
2 times line log.
and then you have a 2 times line log from x, and then
three.
x log. Is that clear?
Yes.
Yes. Let's
So I'm going to do the same thing.
Now
I'm going
there's 4.
We're gonna have 3.
No. Okay, there's
GG.
3.
Right?
Yes, think.
Now what's the next step?
Next 2.
But here is 1.
We took the derivative of this guy now.
2 times.
Do the next
Now
one.
what?
Blob dash blob square.
So we have blob dash blob squared.
Factor
Line
3.
law. Factor of 3 here.
No,
Yeah.
that's outside.
I took it.
Can I just?
No,
No, for
that's
this.
from the first term, right? We have 3 times 2, but we have that second term, man. It doesn't have.
Blob blob
You
you
took everything out.
I took 3 times 2 outside.
Oh, this is still the first term.
First term. I'm
Oh,
taking
yeah.
the derivative of
Yes,
this guy,
yes, yes.
Okay.
keeping this guy
Oh, yeah.
Yep.
fixed.
Yeah.
How do I take the derivative of this guy?
Isn't this gonna be
2 dash
twice?
blobs.
Yes, this has 2 sources, right?
Yes.
So you can differentiate it in 2 ways.
So get 2 out and then you will be dot dot blob.
Correct. So you get a 2 outside, then you have a blob that's going to x,
And it
And
goes
then-
to
and that blob
Itself.
goes to x, which I'm going to draw as
Same thing.
x.
And.
So we have the derivative of blob at x, right?
Yes.
There are 2 blobs, and what this guy does is to replace a blob with a space-time point, and the space-time point here is x. I can do it in 2 ways.
So
Let me do it
twice.
explicitly.
Yeah.
So if I take a derivative of this guy, I get x boom boom blob x plus. If I then take a derivative of that guy, I get blob x x, right?
Okay.
This is just flip each other. So I will put a factor 2 here and forget about that. This x goes to itself. So I write it as 2. Boom.
This is so cool.
You will not get it in any textbooks.
Probably. Yeah. You need a red texture.
So that's clear, right?
Yeah.
Now let's
Now
Oh.
close it.
We have to do the next term.
2 times boom x log. That's it. Can I erase this? Did you write it down? Did we complete the derivatives?
Yeah.
Close
No, we
it.
said
For
the
the
other.
first term we did, right?
Oh, we have to do the other one.
So the square bracket closes,
Yeah, now the next one.
plus square bracket opens,
So,
and what's the derivative of that?
3 blob blob
3
square.
blob square
2 times.
2 times x to blob.
2 times
dash blob.
x blob, right?
X to blob.
And I put the x blob on this.
Balloon.
Yeah. it's a
With the
balloon.
string.
Is that clear?
Yeah.
Should I go slowly or?
There's no way to connect something to blob blob, right? Because it has an X.
Yeah. What is it?
Like, you have two things that combine them.
Yeah.
And you can't combine anything with blob blob.
How
Because it doesn't have any
X's.
x index. So
Oh, I see.
now that's all. If I take a derivative of this guy, it's 0. It's a constant. So the square bracket closes, the curly bracket also closes. Now let's go further.
We have the other term also, right?
Yeah.
constant.
This term,
Goodness did.
Yeah.
that doesn't have any blobs. That means it doesn't have any sources. So if you take a derivative with respect to a source, it's 0.
No source, derivative with respect to source is 0.
Yeah.
Okay.
It's just like
dx by dt. No, d Spanish.
take a constant
D
and
constant by dt.
Yeah, I mean,
yeah,
just, yeah. It's,
or
it's dx
partial
by dt.
dy by dx.
Yeah.
Is equal-
Okay.
partial
dy by
f-
dx. Whatever.
I mean,
dx by dt is fine.
F of 1,
this
dy,
is
dy by
a
dx
bit
of f
more
of 1.
complex because you're taking the functional derivative and j is a function of x.
Yeah.
But when you take the derivative of as such, when you don't have
j in
j
it,
explicitly,
it's zero.
then yeah, it's kind of taking a partial derivative from a function.
Yeah. Let's go to the next term. Where should I write it?
One last differentiation to go.
This is gonna be PQ's next homework.
Yeah, this can be.
So
I'm a bit curious, like why you chose this particular diagram or like vertex.
oh yeah, I have to get the
Yeah.
you'll get it
Okay.
immediately.
Can we just like combine them? Or you wanna keep them separate?
We can combine them, but should we keep them separate or combine? Let's combine them.
No.
4
Is that possible to combine?
x
Or the last two terms?
yeah
You can
x.
take factor of 4 out.
Yeah.
Let's see. This is 3 2 2 2. That's 3 times 2 cube. Log times log. Plus, somebody please combine it for me.
It will be 3 times.
3
6 plus. Do we still have 3 times 4 out? No.
There's a
It's
3
3
times
3
2.
times 3 times 3. Wait, no.
There's
No, no, no.
Three times.
Three
It's
times.
okay.
It's 3 times.
So there's another two one there, right? 3
No, so
times.
it's 3 times 6. 3 times 4 plus 3 times 2.
3 times 2.
So if I take 3 times 2 outside, then I have 2
Total
plus
of
1.
3.
3.
3, 2. 3 times 3 times 2.
Yeah.
Oh, for the
3
next one.
squared times 2
Mm-hmm.
log squared. Right? I think that's right. Let's assume that. Now let's take the last derivative. That's 4 times 2 integral x.
Should be 2 squared in the last one.
2 squared?
No.
It's 3 times 2, 3 times 2, then you have 2 plus 1, that's 3. What?
How did you get last time? Seriously, I didn't get it.
This term?
Yeah.
So you have a 3 times 2 times this thing.
Yeah, that term and that term are.
This term and this term are the same, right?
Yeah.
So what's the prefactor of this term? It's 3 2 2.
Oh, it's outside. Yeah.
And for this it's 3 2. So it's 3 2 times 2 plus 1, which is 3 square root. Right? Now let's take one more differentiation. How many derivatives? One. Yeah, okay. Somebody start reciting.
Go ahead, Suji.
It's 3 times 2 cube, and the bracket opens. Now what?
You
Just
get
one
your
thing.
desired diagram with a factor of
The 4
Two.
globe X thing.
with a factor of 2.
But with
So it has a factor of 2. If I take a derivative of this guy, I get a factor of 2, and then
Dash. Or 4.
Because it.
right?
And
Yes. Plus, I keep this guy intact and take a derivative of the other one, which is log, then what?
can you delete the rest of stuff?
Yeah, you can erase this, right? Yeah.
But I need these factors. Somebody can you write it down?
I have it.
Wait,
You have it?
Yeah.
I cannot do logic. How did you combine the last two factors there?
So you have a
So it's 3, 3,
two and then 2, right?
It's
and you have a 3, 2 here. So it's
So
3
plus
times
six.
2 times 2 plus 3
Yeah,
times.
so let's look at what is, oh, no, okay, so this 3 times 2 only multiplies the first, okay, no,
Yeah,
I
the
understand.
square bracket closes.
Yeah,
I was careful to put the bracket.
that's true.
So let's take a derivative of
Yes.
this thing. What's the derivative of that thing?
Yeah,
3 times.
It's gonna be down, but then,
Oh,
One
loop,
loop and
loop and 2
blobs.
blobs.
Yeah, it's loop.
Two blobs on one side.
So 3 times 2 blobs.
And
Three
2
times
blobs.
two.
Yeah, exactly.
And she's writing it straight.
And the factor is what? 3. 3. Because there are 3 ways you can take a functional derivative on G. Right? Now, that gets.
that closes the
That
first.
closes the bracket. Plus 3 squared times 2. Bracket opens. What else?
2 times.
So two
2 times a dumbbell.
blob.
2 times a dumbbell.
And 2 times.
Times that last.
No, so you do loop blob.
Times 2.
Times 2.
Shut.
No, one block, 2 blocks.
Okay, so
Right?
Mm-hmm.
I forgot the two.
Now what?
Less an 8.
Blob 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 squared. And
Then one more.
Just a
Eight.
loop? Is it a loop?
One more loop.
That is vacuum.
that's a vacuum bubble. Which
Wait,
is
how did that happen? It's a derivative with respect to the source?
yeah, and you connect this thing becomes x.
So I'm okay, so you just move it to x. I don't
Yeah.
understand how it becomes an infinity. I'm sorry. No, I don't understand. I don't understand why there are 2 loops now.
You understand this becomes this, right?
Yeah, so
So
X goes to
x goes to x, right? So x goes to x.
ooh,
Catch the movie.
that is
Time
some
to
bullshit.
connect.
No, I mean, if you took the derivative of a blob and x, what do you get? X,
A
right?
line.
And you just close that up.
Yeah.
That's a loop. Same thing happens here.
That's 2 loops. That's not a loop.
So
No,
it is.
yeah, it is 2 loops.
It is
Yes.
the loops.
X,
But if they're connected at the same point.
x.
Yeah, what's the difference between those 2 loops attached and just one circular loop?
What do you mean?
In this case, not. If,
No difference.
maybe you asking this,
So let me think.
the difference between this and
Yeah,
8.
let me just draw it.
Yeah, right.
This
Mm-hmm.
and just this.
Oh, yeah. This is delta of x minus x, right? 1 over I.
Oh,
What is this? This is 1 over I delta x minus x
Square.
squared.
hmm.
Still don't see it?
I mean, I see it, but only if you can just, only if, there's, I don't know, man. I see it, but it's kinda annoying me, because there's no reason why, I don't know, the loops can overlap.
Sure, you can.
Yeah, they can, right?
That's why there is square, right?
That's
Yeah,
also
yeah,
fine.
that's
That's why
fine.
that is correct.
It's just
It's
some
same, right?
notation.
It's the same.
That's the same thing.
Yeah, that's right, yeah.
But this is traditionally.
But you can see the how many are there if you overlap, right?
Yeah.
Yeah, I know. Sorry. I love that.
So the bracket closes here, right?
Yes.
The big bracket also closes. So we have successfully computed everything. So let me put in these factors in front, which is just now can we combine some terms?
Midterm.
Okay, so somebody combine it for me.
It will be 3 square, 2 square.
Yeah.
No, wait, 3 square, 2 thirds. And 1 more 2.
Let me just complete writing all these things. Then what?
Do you have anything outside brackets? No. 3 square, 2 in a factor of 4.
Yeah, basically, 3 squared to the 4.
Yeah.
I'm trusting you guys. I don't see it at all.
It's 3Q.
Oh,
Two,
3 square goes out for all of them, 2 third also goes out, and there are 1 plus 1 left.
Yeah, pull the 3 out, right? So you get for the second
First one has
right?
3 times 3, 2
Yeah.
thirds.
Yeah, it's
And
good.
3 second, 2 thirds.
I don't see
and just
anything.
combine.
Just call the diagrams ABC, it'll be easier.
Yeah.
Just forget it.
Plus 1.
Okay.
Plus this guy, which doesn't have any factors apparently.
No,
has
no,
this
it's
3 squared.
3 square 2 is this factor as well.
3 square.
3 squared.
2 squared, 6 squared. 18 cubed.
Right?
Yes.
Now we make up a new rule,
No.
which is if I see I lambda integral x, just that, it's replaced by that. If I have a vertex that connects 4 legs with no specified index or space-time point, I assume this.
Uh,
No specified what?
what's that?
So
Like there's no blobs, no x's.
no blobs, no x's. If I see this, just this, that means
Basically integrate out the space-time point.
yeah, we are integrating it out. I don't want to write the integral, that's the point.
No, I mean, the notation, I'm just saying. Yeah, I can just take it, you integrate over the space-time point, it's gone.
Wait,
That's it.
you did with like the big x thing, so if I have x in the center, blah, 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 and I integrate it.
This one, right?
Yes.
Yeah.
Will I get blah, 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 nothing?
Yeah, I will drop this integral symbol and I lambda, that's all.
And drop the x's in the centers all over
Drop
the
the
place?
x in the center.
For everyone.
So it's like, it's included, right?
Yeah, yeah,
And
I'm
it's
just
like kind of
making up a-
notation stuff.
I'm making up a rule. So this.
But what happens when we do that with the dumbbell?
Also
Like
the x, right? On the right
Nothing
hand
It has
side.
to be cross in the.
Cross in the right hand side.
This?
Yeah.
I'm just dropping that. Deliberately. If I see a vertex, I replace it.
Just remove the x's,
Yeah.
specific dot.
Sure.
Why?
Because
Like
that's.
you say you make a rule, but like, it
It's
should make
just
some kind of
convenience.
sense.
So in that case, for the integration, you'll just throw it away and you'll put the x over there.
Yeah.
Yeah,
But yeah, okay.
it's just convenience.
Oh,
Uh, There's no particular reason. I think fine we came up with this. So in that notation, this will become T14. What? Let's see what it becomes. If I don't have to write.
I think the reason is just because physicists are lazy and they
Yeah.
wanna write like z equals to some diagrams, not integrals of diagrams, which are
Yeah.
even more difficult to explain. If you're just coming up with diagrams by themselves, why not make it shorter
Yeah,
to simplify it?
Yeah.
we just need to know like what kind of.
So let's rewrite this in the full glory of Feynman rules. So we don't have this I lambda anymore because we've taken care of that in the rule. The factorial terms still are there. And
Straight 2 and jump by 2 to the 4th.
and then
let me
4 to the
put this guy inside.
Okay.
That gives me a 4 factorial times 2 to the 4.
Yes.
Yes.
Yes. But I think it's better to take out 4 factorial.
Yeah, I'm going to cancel the factors. Right?
Yeah.
This just means this. You when you see this, you replace it.
Are you
Yeah.
deliberately not writing x at the vertex?
Yeah, that's a rule, right?
But see, the integral is gone.
If the dot
Mhm.
has no specified index,
Mhm.
it means that there is an integral x.
Yeah.
So I'm not writing the integral x.
Yeah.
Hence, I'm not writing as not specifying a point.
Okay, you
If I
remove
don't
the dot.
specify a
Okay.
point, that means it's integrated over. Just like what we had here. If I don't specify an index on the source is integrated. If I don't specify an index on the vertex is integrated. Right?
Right.
Now what? What's the next term?
We get a 4 factorial times 3 times 2 to the 4
Something else.
4 factorial times 3
times 2 to the 4.
4 and then what?
Log, log,
Log, log.
log, 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 without S.
No x here. No integration.
So if I integrate log, log, just log, log,
What?
you started this one, not me. If I have integral of log, log,
Integral of this
That's
guy.
my x,
Yeah.
right?
yes,
Yeah.
it's just log, log.
Yeah. I'm not specifying any index on these,
So
right?
it just will be log, log.
It's blob and it's an integral. There are two integrals actually.
No, inside I understand. I mean like I lambda integral over x log, log is equal to log, log.
That would be defined as this because you are integrating all over space time.
Yeah, that's what I'm saying, like-
Propagative between two like sources.
The fact that there is no.
That's what I'm asking. It kind of doesn't make sense.
Yeah.
Like,
I'm trying to understand your question.
I do.
What is your question?
can you write down in I lambda?
What happens if
Mhm.
we integrate x over 2 plus that log, like.
Oh, but there is no x in the middle, right?
Yes.
So you
I guess say that again, I
I
You
lambda
integrate in a constant.
integral over log x
Integral over constant, yeah.
log line log. What that equals to?
Doesn't mean anything. It's just
But in math appears like,
So
So the number is just like a constant for that. There needs to be another term.
yeah, that's what I'm saying. Like, it's kind of constant. And what if we need that, or we will never need that?
you'll never need that.
Okay.
Oh, therefore. Therefore.
Yeah, what's the next term?
yeah, the issue is you only see an integral whenever you have a vertex.
Yeah. The integral x
You
comes
do not have a
by construction of the rule. You see integral x only when you have a vertex. And when you have a blob, you have an integral, but that's taken
But
care
that's
of.
inside the well, I got that.
Yeah.
Okay, you have 4 factorial 3 times 2.
4 factorial 3
Times
Okay.
times 2 of what?
Log, log square
log
and
square.
root log.
And still there are no x.
No x. No x.
No x's. Now let's cancel the factors out and
You're not canceling that, so.
Still do it.
Not like you.
so I get 1 4 as all of these cancels except the 1 by 4 factorial.
Yeah.
This factor I can guarantee you, is that right? Plus what?
3 times 3 over 4 factorial.
So it's just, no, it's just,
3 over 4
3 over 4
factorial.
no, just simplify it further, right? Multiply by 4 and 2 and divide by 4 and 2. So you can cancel everything outside, so you just have 1 over 8.
1 by 8.
Oh.
Everyone sees algebra differently.
1 over 8. That's
Yeah.
better. I think. Yeah. Okay. Log
log, right?
Yeah, plus 1 by 4,
Yeah.
Plus
1 by 4,
No.
1 by 4, 2
No,
to
we
the
need
4.
2 over 4.
2 to the 4
We
is
need
120.
32 and 4. 32 times 4. So 128. 1 over 128.
what's the factor?
1
Over
over
120.
128.
Yeah,
Can you say that in terms of some 4 factorial?
Yeah,
or
you
something?
better correct it some other way.
2 to the power of 6.
160.
128, just right.
512 gigabyte.
I understand it's 128.
It's one by 64, right?
Isn't it
let me check. So,
4
it's
factorial
times 4
cancel.
divided
It's
by
16 times 4, it has to be.
Let's check.
That is
No,
64.
It has to be
64.
4 plus 9. No, no, it's
Eight
not. You're getting
times-
No, it's 2 in the degree of
8 times
6.
4, right?
2 to 6.
It should be 8 times 3.
Okay,
Isn't it
2 to 6. It's just right. 2 to 6.
Ravi, just write it.
No, yeah, but we try to check if
No, no,
the
if-
factors
Okay.
are right.
No, no,
Like
if
if they're
it's
supposed to be there.
just
Those
write
first
the-
two are right.
Write the calculation so that we are not confused.
Yeah, write the calculation.
Cancel 4 factorial.
Okay.
I'll do the calculation.
This guy goes,
Yeah.
Yes. 3 times 2
It's 1 by
cancels 4
64
factorials
actually.
and 4 is left.
That's 1 by 64.
Yeah. Okay,
Multiply by
I
4
multiplied
divided by
2
4.
to the 6 wrong.
I get it.
I'm trying down the right.
It's just 1 by 64, right?
Yeah, multiply by
Now
4
cancel it.
I cancel it. That's the minute right to the right? Let's see.
It's 1 by 64, man.
3 upstairs.
3, cancel it from 4 factorial and you will get 2 times 4.
4.
Yeah, so all together is 1 by 64.
Yeah.
To the power 6. It's to the power 6.
No, I want it in a specific form.
Which 4?
Yeah, tell us, we will
Like
fix
1
it.
over 8 you like, 1 over 64 you
We'll
don't
we'll make
like.
it for you.
Decide
Can we
which
get
one you like.
this form?
I'm trying to compute.
Then you need 3 on top.
3 on top.
24 into 3.
I think
Yeah,
it's
you
this
need
form,
3
isn't it?
on
You
top.
were supposed to
What
get
you
that.
trying to do? What
Did
you
we
like
mess
to
it up?
next?
Mess it up?
No, because I know the answer in
Yeah.
a different way.
In a
Yeah, we shouldn't have then 3
So
three
it's
terms
3
over
over
there.
4 factorial.
Then you shouldn't have 3 over there.
There's no 3 here?
3 over 2.
If there is no 3, then it will.
Oh, yeah, that is true. There is a.
But
What is this?
maybe we messed up previously.
Is it?
What is this?
If you messed up there, the rest is also messed up.
You may mess up
Probably.
some factors in the middle, I think so.
Probably, okay. So
Wait.
let's
It's
move on.
fine.
Now let's
We
move
don't
on.
wanna move on, cause.
Because
who wants to
this is
talk
how
about
you get the
symmetry
symmetry
factors?
factors, which I wanted
It's
to get.
important.
Assuming we messed up the derivative somewhere.
No, we didn't mess up the derivatives.
Counting of these factors in the derivatives, we lumped together those terms, right? So there must have been error there.
Yeah.
He probably is gonna talk about it.
What?
She's asking how can we guess that
Wait a
this
minute.
was.
It should be 3 squared.
So this is the factor, how to get there?
How do you know it otherwise,
Oh yeah, that's the thing.
By the way, there is
talk
3
about.
square. Ravi,
Yeah,
there is
that's
3
what I'm
square.
looking at. Where is?
Is it
No,
3
no, there's
No,
3.
no,
No,
no.
don't put it there.
That's not 3.
He took 3 out somewhere and made it. Delete it. It's wrong.
Yeah.
No, there
He
is.
took 3 out. You took one pair
How?
of 3
How?
from each of them out to combine it with 2 and 4 and make it 4 factorial.
Yeah.
There shouldn't be a 3.
That 3 already exists
That's
in that.
3, that's
That's
3.
So
square
that
is
is just
wrong.
3, right?
Let's go.
Okay, do one.
A square is just 3.
Just do this calculation. That's the easiest thing. Multiply it with this and this.
What?
Oh, he took like
What-
3 from each
Yeah.
of them
Right.
outside and
Oh.
combined it with 2 and 4 to make 3 factorial. So
No,
that's
just-
3 to 4.
You see,
Three
getting
just
to
do
2.
it.
3 left over
He
there.
separated one of them. He took
Yeah, just do
outside
the last
brackets.
multiplication, Ravi.
Outside.
There
He
shouldn't be a 3
already took
here.
that one
Yeah.
outside brackets.
How am I getting a 3 squared here?
Yeah, that's.
Ravi, just do the last
Oh, you
calculation.
use one of
true.
these
That's true, I
3's
see
to
that.
get 4 factorial.
Yeah.
It shouldn't be having the 3 square in the first place. It should have just been.
That
3.
could be. That,
Yes,
yeah,
that's-
that's.
So is this the correct term? I said I trust you guys, I didn't.
Yeah, that's what I've been
No,
saying,
you
right?
have this 3 because 3 to the 2 multiplied by 2 is the common factor for last two terms.
Go there, Diana, and point to him. That's better
Yeah, yeah.
than just saying, just
Yeah.
point to him. Yeah. Assume that this is 3 to the square.
This thing was common factor for both, right?
Yeah.
Yeah.
So we have these 3
Mhm.
2 and 2 here, and then you took each of these, one of each, to combine with that.
Yes.
So it's only one left there.
Right, but that's not the problem. I'm saying the problem is it should have been a squared in the first place.
Why not?
Because that's being problematic in the end.
Oh, yeah, I understand that, but like you
No,
are saying we made
it should be
mistakes.
squared. In
It
the
should be
first
square
place.
because it
should
has
be
three
I
squares.
know, but so that square is coming wrong. So this square.
That
No,
could be
it's
wrong.
not coming wrong, that's the issue, I
We
think.
already did
From
it.
the last. I think what the other is trying to say is this. Assume that,
This factor is also correct.
Mm-hmm.
This factor
Has to be correct.
looks like it's wrong. Let's just keep it what we got. It's 1/2 to the 6, right?
Yes.
Okay.
3 was okay. Like you're taking the right factor.
Yeah.
No.
Oh, right. It was 1/2 to the 6.
That's correct, right?
Mm.
I mean, this is the factor that we got.
Yeah.
but
Yes.
that's- Right? Not maybe. So we, being physicists, we are lazy again. We don't want to memorize these factors. So we come up with a new rule,
You say.
which is something I'm very confused about. So I need to look at what I wrote.
Yes.
So ridiculous. So we had this to start with, right? The v factorial. Gave up.
Why don't you look at your note, like what factor is there because of this?
In my note, I got it wrong.
Okay. Then maybe you are right. The Feynman was wrong.
So let's see. If we have a very general term for any v and p, right? These functional derivatives can be at a vertex. This contributes to a vertex with 4 lines. You can rearrange the functional derivatives in 4 factorial ways, right?
Yes.
At each vertex. You
Okay.
can rearrange the functional derivatives in 4 factorial ways.
How can you arrange 1, 2, 3, and 4 in different sequences?
4 factorial.
That's it.
factorial.
Just so how you have 1 over d by dx, 1 dx, dx, dx.
So
But the order of the derivatives.
Yes.
yeah, I mean, you can connect the first one to the y point, or the second one to the y, and so on. And at each vertex, you have a 4 factorial here. So that 4 factorial boom boom cancels at each vertex.
Okay.
And if you have v vertices, you can rearrange those vertices any way you want. Why is that? Because if you have v vertices, this thing is integral x1 blah blah 4 integral x2 blah blah 4 blah 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 integral xv blah blah 4, right?
So
And
v
these
factorial-
integration variables are dummy, so you can swap them around, which will give you a factor of what?
v factorial.
V factorial, which cancels with this v factorial. And likewise, if you have p propagators, it will give you a factor of p factorial. You can rearrange these guys in p factorial ways and it cancels off with a p factorial. And if you have two sources, how many ways can you rearrange? Two ways. That cancels off with this 2. So everything cancels. But that's in a naive calculation. If we have say some rearrangement of the derivatives give you exactly the same rearrangement of the propagators, for example, then you shouldn't cancel both factors.
You have overcounted.
You have overcounted the overcounts. Forget it, you've overcounted, that's enough. So that's where the symmetry factor comes in. So let's look at the diagram. I have to figure it out now because I don't really understand it myself.
Can you repeat what you said for the sum over p again?
Sum over p.
Yeah.
So if you have p propagators, right, you can rearrange it. P factorial ways. That p factorial goes with this p factor.
Okay.
And you have two sources at the end. You can swap them. That gives you 2 ways, and that 2 cancels with this 2. So every factor cancels. P factorial cancels. P factorial cancels. 2 cancels. Everything cancels. But if some swapping of the derivative, say at a vertex, gives rise to the same diagram as the swapping of the propagators, then you shouldn't cancel both the factors because one cancellation accounts for both. So you've overcounted.
Ah, okay.
How do you look at it? That's the thing. Now let's find the symmetry factor for this. The symmetry factor is the factor that we have overcounted.
So it's basically counting the number of ways arranging one gives the same permutation of the other.
Yeah. So I'm not really sure about. Let's look at an easier diagram. This is not a QFT problem anymore. This is a
Permutation and combination problem.
So at this vertex, I can rearrange the derivatives in 4 factorial ways, right? But I can rearrange these propagators also in 4 factorial ways, which gives me exactly the same thing. So the factor for this is not, so the factor for this is just 4 factorial.
It's not 4 factorial times 4 factorial.
Hmm?
We would naively think it would be 4 factorial times 4 factorial.
Yeah, but we shouldn't cancel both 4 factorials. One 4 factorial should be downstairs, which is boom.
So fix the propagator, rearrange the vertices.
Yeah, I think that's the idea. If somebody knows it better, you can explain it now.
You said fix the propagator, fix the line, put the things in different places.
Yeah.
I was thinking in the other way, fix the vertex, shuffle the problem.
Yeah, which is also
Same thing.
Same thing.
Yes. Now let's compute the factor for this guy. This is where I get confused. Can somebody?
Do you need color checks?
No.
So how can you shift the vertex again?
So you can. That's I think if you can swap the vertex factors here, right?
Okay. So 2
But
ways.
you can swap these propagators also.
So you can
2 factorial into
2.
Let's do it explicit.
Which is what I did. I got it wrong.
You can swap the propagators, that's 2.
Yeah, swap the vertex of these 2, that's 2. And swap the vertex of this guy, that's also 2.
Swap the vertex off.
This, you can connect it this way,
Oh.
that way.
So it's 2 times 2 times. Swap the vertices this way, swap the vertices this way,
Yeah,
swap the
propagators, that's 2 times 2 times 2.
Yeah.
We should not cancel all the 2's. We can only cancel 1, 2 because
So
all of them
this-
give the
this-
same diagram.
So this swaps the vertex and swaps the propagator as well.
Yeah, all of them are the same diagram, right? So we shouldn't cancel all of those 2's.
Here,
That's the idea. So what's the leftover factor?
it's 1 by 2.
No, it's 4, right?
4.
Did you get it? Don't get it.
It's actually a bit tricky. So you can swap these 2 propagators.
Yes.
Yes.
Factor of 2.
Yes.
you can swap the vertex of this connection and that connection, factor of 2.
That's equivalent to swapping the propagator.
Yeah, you get the same diagram back. Now you swap this end. There are two ends, right? This end with that end. You get the same diagram. That's a factor of 2. So we have 2 times 2 times 2. And all of them gives you the same diagram. So in the name of this v factorial or p factorial, you shouldn't cancel all of those 2's. You should cancel only one of those 2's.
Okay, Ravi, you said the swap the propagator and vortex. What is the last one?
The end of this part.
At the end of loop is the vortex, right?
Yeah. But if I swap the ends of this loop propagator,
Okay.
I get the same diagram.
What is the swapping the vortex then? I mean, how to, isn't it the same thing you're saying?
Yeah. If I can swap the vertex for this connection and that connection.
Oh, okay.
This
I
connection
see.
and that connection as well.
I see.
It's very confusing.
There must, yeah, there
Let
must
me
be
give
better.
Let me give
Can you
a
give
rule.
an explanation for S?
Actually, we know.
What's that?
What S means? Like,
Oh, S is the factor I put down here.
I understand that it's a factor you put down there, but like,
It's
more
called the
physically what it is.
no meaning.
It should have meaning, like, is it the number of ways I can build it or something like that? It should
Yeah,
be
it's
something like
the
that.
number of rearrangements that gives you exactly the same thing. I think.
Sounds
Is
like
that
a
it?
degree of symmetry of some.
Something like that, and
Yeah.
I think that way would be easier to understand. If we
Easiest
understand what it
way
is.
is the following.
So why are we finding the symmetric factor? Because is it because there is another way where we can draw the
Yeah,
diagram without
to
going
get
for the
these,
calculation?
we have to do a lot of jugglery, right?
Yeah.
We can skip all that. That's the idea. So the easiest way to do it is this. Let's consider this then. And let me put an X over here.
Make an arrow over the loop so that when you sort the loop so that you can draw another arrow.
No, arrow means a different thing, so I don't want to confuse it.
Just for the sake of this particular
No,
example.
this is going to be easy. This is, I call it Gabriel method, because he told me this afternoon. So, let's call this point Y, and this call point Z.
Yeah.
Yeah, but I mean, the way I was counting, you have to remember, it was after taking derivative with respect to.
Yeah, I can add a factor of 2.
Yeah.
So, right, so I have propagated from Y to X, then X to X, then X to Z, right? So I have a propagated from Y to X, then X to X, then what, X to Z, right? How many ways can I connect Y to the X?
4.
4 ways, right? So I made one connection, I can do it in 4 ways. Now, how many ways can I connect X to the next X?
1, 2.
2 ways.
Okay, I didn't get it. X to the next X. How is it 2?
I didn't get the full thing.
Oh, you just. I get it. You have to go.
How
I
many
get it.
ways can you connect Y to?
How many ways can you hop to the next one?
Are you
Right?
trying,
Yeah, next X.
Are you trying to do Wick's theorem?
Yeah, this is sort of Wick's theorem.
Yeah,
Then
Yes, like-
then you gotta do
operator formula, Z to X.
you gotta do Y to X and then Z to
Z to
X
X, I
first.
think that's.
You can't do X to
Oh.
X.
Oh, is that so?
Yeah, because X, the other X that before you contracted, after you contracted Y to X, can go to either one of the other X's, but also
Or
can go to Z.
That's true, yeah, that's true. So how many ways can you connect Y to X's? That's 4, right?
That's
Yeah.
four, right?
So if I try to connect X to X's,
Then
the next X can also go to Z.
So it's the same thing that they say, it will always 3, factor of 3.
It's a
And
factor of
X to
3.
Z or Z to X, it's both 3.
Yeah, so to avoid confusion, let's connect Z first, which has a unique connection. So from Z to X, how many ways can you do the connection?
4.
Wait,
Three.
one is already.
Oh,
That's
this one is
one.
fixed. Okay.
Oh crap, man, that's
And three,
stupid.
right? And this x has to be connected, there's no more ways. So, and at each vertex you have this factor, right? And this is the number of ways we can make these connections. So you multiply this by the number of ways. Right? And since we have two sources here, we can rearrange the sources as well. Right?
That means y can be z and
Z can be y.
Yeah. So,
So 2 into 4 times 3.
no, I should divide by 2 now.
Yes.
That's the degeneracy.
That's a degeneracy.
Okay. Oh, I see. Yes. Yeah.
Right? So what do we have as the factor?
1/4.
1/4. Which is,
You need 1/2 from blob.
yeah, this blob will have a factor. Now let's look at the factor for this guy. So, what is this? Let's call this point x.
You have x, which
Yes.
is
X.
it just
Ravi, there's one question. So in the previous one, how did you get them? So you wrote there like y, x, z.
Yeah.
I understood like you write y and z, but there shouldn't be only one x. How did you get the 4x over there?
So it's just, I'm just tracing out the path. Y goes to x, y goes to x,
Okay.
x goes to x, x goes to x,
Okay, I got it.
right? All the propagators, I'm just writing down the propagators. So here it's x to x, then x to x. So x, and then don't search that on the internet.
That's like a
What?
Then it's 1.
Then it's 1, right? 3 times 1. And you have a factor of 4 factorial coming from the vertex, which gives you.
Sorry, I did not get why isn't it 3 times 1? I thought it should be 4 times 3 because like you have on the vertex you have 4 like lines going out.
Yeah.
You can select any 2 of them in 4C2 way.
You can select any 2 of them and 4C2. What is 4C2?
Then it is 4 into 3 divided.
But they're all the same.
Answers, right?
Both are the same.
All 4.
So you have to divide by 2 as well, right?
I thought C is just when you have the same thing twice. Oh no.
But you're selecting
Twice comp.
pairs, right? So, but they are not distinct pairs, they're the same
Also,
pairs.
even if it does not matter which one you take, so 4
Yeah.
won't be there.
So you would divide by 2.
So 4C2 by 2, which is what?
4C2.
No, not
6,
divide by
3.
6.
3,
Yeah, which is what? Yeah, right?
3, yeah.
And the 4 factorial comes from the vertex.
Yeah,
And
what are you trying to do again?
So he said there are 4 lines going out of each vertex, right? So there are 4C2 ways of selecting those pairs, right?
4, I chose 2 by 2, yeah.
Yeah, but it doesn't matter, it's AB is the same as BA. So you divide by 2.
and this is, I can't compute this, man. 1 by 8. Right. Alright. So that's why I was saying that this should be 1 by 8, and there are 4 sources, right? There are 4 factorial ways of arranging it. That's where I got this from.
No, but 4 factorial ways, 2 to the. Each source can be arranged in 2 ways, right? Rearranged in 2 ways. So there are 4 sources.
No. So we'll try to compute things like the expectation value of phi 1, phi 2, phi 3, phi 4, right?
So the sources.
Just think about what we had in the Wick's theorem.
Yeah, sure. Yeah, I can see that if you have 4 things in a line, you can arrange them 4 factorial ways.
No. You remove these sources by computing the expectation value. 5, 1, 5, 2, 5, 3, 5.
You're just
4.
talking about the last 4 factorial factor you put down.
Yeah, I'm just explaining that. So when you compute that, each functional derivative can hit at the first glance the four ways, then you have 3 left. So 3 ways, 2 left. You see that, right? I think it's better to worry about the symmetry factors after we removed
Yeah.
the sources.
I was thinking about exactly about that,
Yeah,
because then we don't have to come up with this whole
additional
terms and, I mean, divide by 2 there,
Yeah,
all the other stuff.
that we can do next week.
Yeah, because the external lines will be fixed.
I think it's a good time to take a break.